Hello, everyone. Welcome to the 100th combustion webinar. So I am Peng Zhao from the University of Tennessee, and it's my great honor to host the webinar. So let's first have Katerina, our first speaker, to give an opening speech to celebrate this 100th milestone.
Yeah, okay, everyone. I'm very happy that we have this event. When we started it, it was time where we could not meet personally and where this webinar was set up to keep the community connected. And I think it worked great length and great time, over 100 seminars, and also over this YouTube channel to find out what combustion is really about. And we've had eminent speakers, and we have one of those today. And so without further ado, I think we will start today's session, but everybody, please commemorate this market event.
That's great. Thank you. So next is my great honor and pleasure to introduce you our distinguished speaker, so Professor Yiguang Zhu. Professor Zhu was actually the founder for this combustion webinar back in April 2020 in a pandemic period. So right now, the combustion webinar has become a major platform to disseminate science among this community of combustion engine fuels and power propulsion. And also it has become a major education platform to disseminate combustion and energy-related knowledge to the general public. So before this webinar, I was checking that our YouTube channel already has 2,240 subscribers, and the total video has go beyond 110,000 views. Okay, so that's really a good milestone. Okay, I really want to take the opportunity to show appreciation for the great leadership of Professor Zhu, the great efforts of all the speakers and organizers. So although I don't think it's necessary for me to introduce Professor Zhu, but still I will do this. Professor Yiguang Zhu is a Robert Porter Patterson Professor in the Department of Mechanical Aerospace Engineering at Princeton, and the director of DOE Energy Earthshot Research Center for Plasma-Assisted Hydrogen Production, the head of Electromanufacturing Science and associate faculty at Princeton Plasma Physics Lab. So he received his bachelor's degree from Tsinghua University back in 1986, and his PhD in mechanical aerospace engineering from Tohoku University in 1994. He was appointed as assistant and associate professor at Tohoku University from 1995 to 1999, and as a Changjiang professor and director of Thermophysics Institute at Tsinghua in 2000. So he joined Princeton University in 2001, and Professor Zhu's research interests broadly include combustion, e-fuels, propulsion, plasma chemistry, and electrified manufacturing for industry decarbonization. He has published more than 300 journal articles. He's a fellow of AIAA, ASME, and inaugural fellow of Combustion Institute. He served as the chair of the US section of Combustion Institute and in the National Academy of Science Steering Committee for NASA. He has received many honors, including the Bessel Research Award from the Von Humboldt Foundation, AIAA Propellants and Combustion Awards in 2021, an Alfred Egerton Gold Medal from Combustion Institute in 2022. He was also a plenary lecturer for the 38th International Symposium on Combustion and received the Distinguished Teacher Award from School of Engineering and Applied Science at Princeton. So with that, let's welcome our speaker, Professor Zhu. The time is yours.
Thank you, Peng, and thank you, colleagues, for the strong support. And I'm really honored to give this 100th combustion webinar after Katerina gave the first one. And so thank you very much. So let me share my screen. So first of all, as Katerina just spoke in the beginning, combustion webinar started at the time of a COVID-19 crisis, and it was difficult for combustion research as well. So now that COVID is gone and combustion also entering a new era, involving green fuel and biofuels. And the webinar already reached 100. I want to say that a big thank you to the members in organization committee, particularly Wenting, Peng, and So, and Yiguang. And you guys spent a tremendous time and to establish this wonderful platform for combustion research. Big thank you again. So let me start by thanking the people who work in this area. And starting from Wenting graduate, I started a plasma-assisted combustion. Today I do plasma electrified manufacturing. And it was them that initiated this project and make today about my research platform in green manufacturing. And I also like to take this opportunity to thank my colleagues who collaborate with me in the plasma research area. And that really make that my research interesting and pleasant. And thank you very much. So the next thing I try to share with you today that what is my personal thinking and about that the opportunity about the electrified non-equilibrium manufacturing and how does combustion knowledge be used. Second thing, I want to show you how do we control non-equilibrium chemistry by using electricity and plasma. And finally, I will show you some of my recent progress and preliminary data about the plasma electrochemistry assisted manufacturing and recycling. And then I try to give you a brief conclusion. So let me start with that what really attracted me to combustion is really that the beautiful flames attracted me to the combustion area. And indeed that the combustion had made a remarkable impact in society and in technology. So I want to say that the utilization and understanding of fire is a history of mankind civilization and industry revolution. And today that is still that 80% of the world energy is powered by a combustion, and probably will far beyond in decades to come. And also that a combustion power rockets reached Mach 10 and already this week, and I think succeeded in self-landing Starship 5. It's really exciting that looking back about combustion and since that the God brought fire to the earth and people using it for to making food and ignite in the darkness and looking for new directions and kill bacteria that threaten our life and the environment. And ever since that the first oil well was discovered in Pennsylvania track, and then it's this picture here. And then since then, and industry revolution came. So at any time when we discover a new energy resource, and there were new industrial revolution to come. So what we are today, that I don't want to scare our colleagues in combustion, but we just try to show you some of the facts and numbers, that the impact of combustion of fossil fuel and really causing that the CO2 rising today is about 400 to 23 ppm in the air, and it will increase 2 to 3 ppm each year. If we don't do anything, it will soon reach 500 ppm or more. And you can see that even though that the number of hurricanes is not increased, but that the scale of hurricane and is getting bigger, and then the impact is getting bigger. So therefore, that the likely that the human-made CO2 emission contributed to an unprecedented change of CO2 in atmosphere, and then likely that climate change as well. So, and the last few years, I keep thinking every year there's some new things happening, and because of this, and in 2022, you can see the lake mead that they ever dried before, and since that ever created in 1530s. And then in last year, in the summer, you see that the smoke from Canada that spread to New York City, and everybody feel it. Why does this happen? It could be because of the temperature rise, Could it be because the CO2 rise that promote that the synthesis, biomass synthesis reaction to increase more biomass, and in the winter time or the fall time, they become more dry biomass, and that is unprecedented. So therefore, they create this wildfire. So therefore, that this something is happening, and because that the mankind activities and of CO2 emission, and we have to find a solution. And if you're looking at IPCC, that International Panel of Climate Change, and they say that over the next 20 years, the temperature is expected to exceed 1.5 degree of warming, unless there's an immediate, rapid, and a large scale reduction in greenhouse, and that 1.5 degree or 2 degrees Celsius increase will be beyond reach. So we will have an immediate action to decarbonize about the energy sectors, and probably in other sections as well. You'll be looking at that clean energy generation, particularly looking for China. So by 2022, and China already established more than 54% renewable energy capacity for electricity. And Europe and Germany in particular, and the US is also increasing renewable electricity. And the scale is also unprecedented. So what happens is that you can see this is very famous California duck curve in terms of net load change, with more increase of renewable electricity year by year, and more deep about this energy load in daytime, and rapid increase in evening time. So we will create a huge intermittency. And even China has 50% of renewable capacity, but they did not produce 54% of electricity because that the intermittency and difficult to store the electricity. And the electric grid really doesn't like this kind of fluctuating renewable electricity. So it's a big challenge, and maybe also a big opportunity. So we should be prepared as that first oil well was discovered. And today that the surge of renewable electricity will trigger another round of industry revolution. May not be fossil fuel, but certainly will be electrification. And where do we stand? How do we prepare ourselves? It is a question I want to talk today. So if you're looking at today that there's a change from fossil fuel energy to some people call electricity, I call electron energy, because it's in a form of energetic electrons. So we will electrify our transportation, and electrify our green fuel production, and we will electrify manufacturing in the future. And we are enabling control about advanced combustion. So to reduce carbon emissions in an unprecedented way using electron as energy sources. So then what is the opportunity? So an opportunity is that you can using electrons, which can be manipulated in nanosecond, and so that you can drive non-equilibrium conversion of chemistry and for efficient and selective energy conversion. For example, you can make electrolysis, make hydrogen, and electrolysis of plasma to make ammonia, and CO2 reduction and e-fuel, and so on. So that also enabling that distributed manufacturing. You don't have to be very high pressure, very high temperature, centralized ammonia synthesis, and can be distributed. And enabling at the novel and non-equilibrium catalysis, and so on. So then the question that as a combustion researcher, we always think that where do we stand, right? If we're looking at the DOE, this picture, the DOE administrator always shows this picture. That is CO2 produced from industry sectors that see chemicals, refineries, iron and steels, and contribute more than 50% of CO2 emissions, and which is very difficult to decarbonize, and has not yet made any big progress. In transportation sectors, electric cars is on the way, but in this chemicals, refinery, and iron, and steel, and food, and we are still on the horizon. So that is a big opportunity to all of us. So the question that is combustion research obsolete? And what kind of, if not, what kind of knowledge gain in combustion is useful in enabling electrified manufacturing? So that's why I want to share with you some of my thought and preliminary result today. So in combustion, one of the big things we learned is that in chemistry, and Katerina is here. And at high temperature, the fuel basically that it goes through this pyrolysis, and then with H plus O2 reaction, and you convert that the fuel into water and CO2. So that we know this a dominant chain branching reactions, and you generate two radicals, and at high temperature, and you produce high temperature flames, and with soot. At the intermediate temperature, I would say that this is that you through a peroxy radicals and peroxide to generate two OH radicals, you branching, and you generate this kind of warm flames. And at low temperature, and you have through this a oxygen addition, for example, alky peroxy radicals, you form this cool flame. These are the milestone change in 5 decades of combustion research to understand completely the mechanism and the dynamics about all three kinds of flames. Congratulations to combustion researchers and to make a tremendous progress. And the question that how do we manipulate it? So I want to say that this is an image for detonation. So my student basically produced this thing and saying that if you have a plasma or using ozone, you can accelerate that this is that the combustion detonation without a plasma or ozone. This is that with plasma, you can accelerate and you can decelerate. So this picture attract an investment from ExxonMobil because they want to do hydrogen burner. They don't want detonation to happen in a small channel. So the question is that how do we actively control detonation by manipulating the combustion chemistry for green fuel production? So all in all, what I try to say is that because we understand the combustion chemistry, and because that we have a way using a radical production from plasma that can manipulate all three pathways and at the temperature and at the time we want by using plasma, that really generate a changing about combustion, particularly today the UAVs, right? A lot of UAVs we require that efficient ignition and flame stabilization at extreme conditions. So these are fantastic knowledges. And for example, that plasma can also, manipulate the reaction rate. For example, O singular D in producing plasma can change a new reaction pathway to form methoxy and methanol radicals and accelerate reaction with 42%. This does not exist if we have a ground state. So all these things I try to share with you today. It is that combustion and gaining a lot of profound knowledge, and that the non-equilibrium plasma can help that to control combustion. So how can we do it using the same way in contributing to electrified manufacturing? All combustion people are familiar with this Van Hoff equations. So for any reaction, you have equilibrium. The equilibrium constant, Kp, is a function of pressure and temperature of product and reactants. So that means you give me a temperature, you give me a pressure, I give you a product to reactant ratio. So the chemical equilibrium sometimes is good, sometimes is bad, because they don't allow you to have a selectivity. They don't allow you to achieve higher efficiency. So the question is that how can we manipulate that equilibrium to non-equilibrium so that increase the efficiency and selectivity? So this is that the diagram I draw when I apply for the ERC proposals for DOE. I said that today that we have equilibrium. Give me a temperature, give me a pressure, I give you the product. But if we can manipulate the temperature as a function of time, if we can manipulate excitation of molecules, if you can manipulate that the catalysis interaction with molecules, you can drive that to a non-equilibrium territory that can probably have a higher efficiency or higher selectivity. So how can we demonstrate that? So to demonstrate that, I have a wonderful collaborator, Liangbing Hu in University of Maryland, now in Yale. He invented this kind of a very thin carbon filter. that can ramp up the temperature. What is going on? So ramp up the temperature in a short time, 10 to 50 milliseconds, and then you let it cool down. So they can up and down and up and down, can manipulate the temperature in a time domain. So that can allow us to do something about manufacturing, for example, plastic pyrolysis. For plastics, if you have a long pyrolysis time, the thermodynamics equilibrium will tell you it will be hydrogen and soot or coke. But if you want to produce ethylene or acetylene, and you don't want equilibrium, you want to cut off. For example, you have high temperature and it cut off immediately, you can form acetylene. This was a hypothesis and around 2020. So can we demonstrate experimentally that this kind of a non-equilibrium heating, simple heating, can increase the selectivity and yield? So this is an experiment and led by Liang Bing, and we collaborate together. So you have plastics, and you can chop it down and using carbon to heat it and melt it, and that will be siphoned to the top and vaporized on the top. And then you have a carbon filter, and then to heat the temperature to several hundred degrees, for example, and then raise the temperature and then reduce the temperature. So thermodynamics from molecular dynamics simulation will tell you that if you heat the temperature a very long time, you generate this kind of pH or generate soot. But if you can heat it very short time, then you can really selectively produce monomers from polymers. You cut the CC bond without hurting that CH bond. So therefore, you recover the monomers by 40+%, and from polypropylene and polyethylene. So this was the experimental result showing you that if you have a polypropylene, for example, then you compare the yield using this non-equilibrium heating and quenching, you can have a close to 40+% of conversion efficiency of monomers. But using classical either pyrolysis or catalytic, you only probably reach probably half of that yield. So this was really that stimulating at the time that when electrified manufacturing, they can drive a higher yield and selectivity by manipulating non-equilibrium. So then we demonstrate another thing. Can we do this kind of reaction, ammonia synthesis? Because this reaction is the key. There are 2 to 3 Nobel Prize in this reaction. This is an exothermic reaction, and it's very difficult to break this in nitrogen. So therefore, you need a catalyst and need a high temperature. But it also exothermic, you need a lower temperature. So therefore, this kind of heating and quenching ideas, you heat it and quench it, heat it and quench it. They will shifting the equilibrium to the right-hand side. You can enhance ammonia synthesis. So in the laboratory, this is that the experiment we collaborated and did, and you can see this is that ammonia yield per micromole and per gram of catalyst power. This is that the different catalysts. You see, Japanese, there was ammonia, a workshop in China recently, and Professor Hosono showed that the lithium nitride nanoparticles can have a highest yield of ammonia. By using shifting equilibrium, even with the simple ion catalyst, we can have equal or even better performance than lithium nitride. So this another indication that manipulate non-equilibrium can enhance the yield and selectivity of critical e-fuels and chemicals. Then the question becomes that as a combustion people, just applying heating and quenching is not interesting. So the question is that how can we enable efficient energy conversion in far from equilibrium using something like a plasma or electrochemistry? So with that thing, I try to pay attention to what plasma can do, right? The plasma, if you're looking at it, is that the fourth state of matter, including ions and electrons. And sometimes plasma, they have a high electron energy. Sometimes plasma has a lower electron energy, depending on the equilibrium. Sometimes plasma is volumetric. Some plasma is contracted. So in order to facilitate engine applications and chemical reforming, material synthesis, or environmental remediation, and you need a different kind of plasma chemistry and dynamics. So the first and foremost important in chemical synthesis to make a uniform plasma so they can treat a large volume that for electro. But how can we generate a uniform plasma? So that was a question. And I try to wake you up in the noontime. I try to say that this is something really stimulated my thinking. So this is the 2019, and before the COVID, I traveled to Asia. And on the airplane, I saw this news. Russia flied a rocket. You can see a lightning hit the rocket, and then the lightning followed that exhaust gas of a rocket. Being a rocket scientist or being a combustion researcher, you understand that the exhaust gas of rocket is mostly hydrogen, CO, and CO2, and some small amount of methane. So the question is really that why does plasma or lightning, they like that they unburned hydrocarbons. So, and then I started Google on the website. I found that the volcano, you can see the lightning flying around. They really like unburned hydrocarbons generate around the volcano. So then my question was that does plasma chemistry and instability is affected by unburned hydrocarbons or combustion chemistry? So with that question, I tried to looking at what is instability of plasma. So plasma sometimes is volumetric, sometimes is contracted. It's because that the thermal instability, just look at the combustion. With the electric field, if you have put a very small current, electric field is high and the plasma is uniform. If you increase that the current, the plasma getting hot and the plasma contracted, become here. And then this you call ignition, this is the combustion. If you reduce current, they come back and then extinction. So this is very typical, becomes like an S curve in combustion. I got very excited about this. And I try to see what is the mechanism. It's very simple. If you have any perturbation on plasma chemistry, that increase of electron number density will increase the Joule heating. The Joule heating will increase your temperature. The temperature will decrease your number density, will increase your mean free path. So electron have more energy. When electron have more energy, it generates more electrons. So this positive cycling just keep going. So then the question is that what if the combustion give you? So what is that to answer this question? What is the fuel chemistry? So I looking back to my knowledge in combustion and coming back to this figure I presented before. If you're looking at this one and all these reaction pathways, they give you different forcing and deforcing about plasma instability. Then I wrote a proposal to National Science Foundation. I say, we know plasma thermal instability. What do you have a fuel? Does the fuel affect plasma instability? So then I wrote this proposal and a list that the fuel ionization, fuel pyrolysis, oxidation, they can either increase electron number density or decrease the electron number density and depend on what process will be. So they will dramatically modify the instability and in a plasma and make it that is uniform or contracted. So luckily the proposal was funded, and then I had the opportunity to work, and I asked my students to do experiment. Compare that the oxygen and argon mixtures with a nanosecond discharge is a very uniform discharge. If we add 6.6% of methane, replacing that argon, you can see the plasma start to contract. And in a few milliseconds. So that gave me, then I looked at the literature, I found that Igor Adamovich and also observed this early in 2020, and showing that when you have ethylene in air, the plasma become unstable, but he never explained. So then I thought there's the opportunity that using combustion to explain this thing. So here that I ask my student now is assistant professor at Michigan State University. I asked him to derive a linear stability equation. It shows that how electric field as a current or conductivity and governed by what? It's governed by plasma chemistry, plasma energy. It's governed by the convection and vibration relaxation, vibration translational relaxation, combustion rate, and combustion heat release, normalized by the Joule heating. If this one greater than 2, plasma will be unstable. If this one is less than 2, plasma will be stable. So we did some kind of computation and experiment variation. Indeed, electric field as a function of current, that if you, this criteria is greater than 2, plasma become unstable. Here it becomes uniform. With this knowledge about combustion and how do they couple with plasma, and we have a confidence that we understand how to control plasma. Then we did an experiment with Yiguang, and you see this is the plasma discharge, and in air, this is that dimethyl ether, which has a low temperature chemistry. So you can see that the instability quickly develop, and when a fuel has a low temperature chemistry. When the low temperature chemistry generate heat and they increase the diffusivity, the instability disappears. This is a very encouraging observation, because that the combustion chemistry affect plasma instability. And then the heat generated by the combustion also stabilizes the flames. So this observation completely changed the people. People always say the plasma chemistry, plasma dynamics is very short, in nanosecond and microsecond. Combustion is always dictated by plasma, but our experiment and theory tell people that combustion chemistry can change plasma dynamics and modify plasma chemistry as well. So this provides a great opportunity that how combustion chemistry or oxidation chemistry can play a role in plasma. So, and then I try to say that how can we build a uniform plasma by understanding the combustion chemistry and that the plasma physics. So in plasma, there is a length scale called Debye length. At the length scale, that the plasma, any change of charge will be shifted. And plasma, equilibrium plasma only happen when the length scale bigger than the Debye length. So what if we create an electrode with a lot of fibers, that each fiber is around a few microns, which is equivalent to the Debye length. So you can generate a far non-equilibrium plasma near the surface, and you can control plasma non-uniformity. So this leads to a observation about that the carbon-carbon electrode, you form a stabilized plasma. And this volumetric plasma has a temperature between 3,000 to 8,000. Then allow you to do some material synthesis. You cannot do it before. Try to show you an example that this is at the melting temperature of materials. This is at the metals, boride, carbide, and nitride. Because we can establish a uniform plasma in a volume, so allow us to make one materials they call hafnium carbon nitride. This materials was computationally predicted. They have a melting temperature above 4,000 Kelvin, but people using arc can make nanoparticles, but no one can make it in a bulk form. So with this kind of uniformity control at high temperature, we can make it probably a 1 inch by 1 inch and a plate. So that is opening a new application in surface coating of maybe gas turbine engines, maybe rocket reentry, many other things. So we created a startup company called US Plasma right now, explore the opportunity of market transfer. So I'll try to give you 2 examples that when you understand combustion chemistry and a plasma, then you can control them and do something you cannot do it before. So the next thing I'll try to show you that how can we control the plasma further. So here that is the thing, plasma sometimes that is very, electron number density is very low, electric field is very low. So we try to using the knowledge materials, for example, ferroelectric materials. The ferroelectric materials is a material that when you put electric field and that the ions, oxygen ions or metal ions can move, so that create a enormous surface charge. So here I show you example. This is a surface charge. This is that the voltage you applied to that the plasma cell. Compared to ferroelectric materials is yellow, and then ceramic is green. If you put a ceramic like aluminum oxides, there's not much surface charge. But if you put a ferroelectric materials like a PZT, and like this is PZT, and then you can see there's strong surface charge, order of magnitude increase of surface charge. So that dramatically change your breakdown, and then electron number density and afterglow. I try to impress you a little bit. So you can see this is that the breakdown of an electric field. And with the yellow one, again, is ferroelectric materials called ferroelectric barrier discharge. And at the breakdown point, the electric field is doubled because the polarization timescale of ferroelectric materials is even shorter than the plasma breakdown. So plasma has another response when the charge is generated, and then you generate enormous surface charge that increase that electric field and increase that the emission from plasma. And more interestingly, it dramatically increase afterglow. If we turn off the plasma, for alumina oxides, that the plasma basically stop. But if ferroelectric, because the polarization of surface, you can see that the oscillation of the charge make you hundreds of milliseconds afterglow still there. You can see this thing. That create a great opportunity. You can generate hybrid plasma using the nanosecond to control that the breakdown. You're using afterglow to control vibrational excitation for chemical synthesis. So you can see this is that the how that afterglow, and the video basically show you that the alumina, you cut off the plasma, everything is dark. But for ferroelectrics, it's continue to glow afterglow. So this really motivated me. How can we control plasma vibrational excitation that for ammonia synthesis? So in the next maybe 10 to 15 minutes, and if I have time, I'll try to share with you how you control plasma chemistry and then can enhance that ammonia synthesis. Ammonia contribute up to probably close to 2% of CO2 emissions. And ammonia catalysis require high temperature, high pressure, typically 200, 300 atmosphere pressure. The temperature typically is 500 C. It's very energy intensive. You have to compress it into high pressure. You have to raise the temperature. And the rate limiting reaction is nitrogen surface adsorption and dissociation. And can we do ammonia synthesis at 1 atmosphere pressure at room temperature with plasma? So that is a beautiful thinking. So with renewable electricity. So here is that the hypothesis people say, when you have a energy barrier, and the combustion people are very familiar with activation energy. So ground state nitrogen, vibrational state nitrogen. If you vibrationally excite nitrogen, and you can reduce the energy barrier, you can accelerate. So this was the idea about using vibrational excitation of nitrogen to do efficient ammonia synthesis. And around a few years ago, around 2018, and Professor Bill Schneider at Notre Dame, he published a paper on nature catalysis. Really excited a lot of people. This figure basically showing you that the catalytic reactivity. This is horizontal, basically show you that absorption dissociation energy volcano curve as a function about that the bond energy. The yellow basically showing the thermal catalysis. And the green basically showing you plasma catalysis. Once you turn on plasma, vibrational excitation of nitrogen, and the reactivity increases by several orders of magnitude. So since then, a lot of people try to, to find how can they increase ammonia synthesis by orders of magnitude. So my collaborator and Igor Adamovich and my colleague that the Brickman all did a lot of this ammonia synthesis. What they found that with plasma catalysis, with plasma, they can only increase the ammonia yield by a factor of 2 with vibrational excitation, no more. And so the reason, what is the reason? What is that missing mechanism? So today there's no clear answer why not. And research always continue to evolve, and the same group that is by Bill Schneider, they using a nitrogen plasma and create a vibrational excitation and nitrogen atoms. And then they turn off the plasma and flow hydrogen at a high temperature. They start to see that the nitrogen atoms absorb on the surface and they run into a hydrogen, dissociate on the surface, they form ammonia. So what they propose that ammonia production is through the N-atom absorption to the surface and play a critical role. If this is the truth, why do they need 60 minutes, 1 hour to activate that the surface adsorption. Plasma nitrogen adsorption or surface only need probably seconds or minutes. You don't need 60 minutes. So something must be wrong, or something is not complete, the answer. So we did some kind of experiment by doing plasma with different catalysts, aluminum oxide, ruthenium oxide, and cobalt oxide. We found that no matter what kind of catalyst, or even without catalyst, plasma can enhance your ammonia just because that the plasma produce NH and NH pathways, they form ammonia. And then the question is, what is that this story about plasma-assisted ammonia catalysis? Is that NH? Is that N adsorption? Or is something else? So is there any kind of hope that plasma can dramatically accelerate ammonia production? So my former postdoc, now is professor at Rowan University, he conducted, to ask him to do it, how does surface charge affect that the adsorption, dissociation of hydrogen and nitrogen? So this is a thermal catalysis. You can see there's a beautiful correlation between ruthenium, platinum, iron, and cobalt, and for adsorption, dissociation energy. What if you have surface charge? So the DFT calculation showing completely different story. So this is their correlation between ruthenium, platinum, iron, cobalt, completely different from the thermal catalysis. If the result is wrong, never mind. If it is correct, that can show you there is opportunity. You can design a plasma catalyst that behave differently from that the thermal catalysis. So this is something that if this is true, not only we can reduce the activation energy by vibrational state, but also we can create a new reaction pathway by reducing the activation energy. And if it is true, how? So then I try to propose a new idea. That is that in a plasma discharge, when you have N atom produced, a vibrational nitrogen produced, the catalysts have a defect, vacancy. Once the vibrational nitrogen see the vacancy, they come in and generate a nitride. The catalyst now from nickel become a nickel nitride. So this I call a name called plasma-assisted Mars-Van Krevelen Mechanism, PA-MvK. And what is the evidence? In experiment, we can see this is that we put a nickel into a hydrogen plasma, you don't see any nitride on the nickel. So you put a nitrogen, you start to see some kind of a nickel nitride is formed, but also see a lot of oxides. But if you're adding a little bit of hydrogen, you get a more nitride is formed close to ammonia. This is a very encouraging that this plasma-assisted MvK mechanism maybe is happening. And then hydrogen can increase the nitridation. Why? If you measure the N atom in the plasma with metal, you see the N atom is decreased. Seems like the N is getting into the metal. So these two experiments basically suggest that electron dissociate or excite nitrogen, and excited nitrogen can react with metal to form a surface nitride. It creates a new reaction pathway, can potentially reduce activation energy. So if it is true, how can we demonstrate? So then we try to look at the literature. There's a paper published 2021 in Delft University. They're using water electrolysis to generate hydrogen, and they're using a nickel nitride to produce ammonia. And when initially they have a nickel nitride, and they will see that the ammonia yield is high and then eventually decrease. And if we understand this mechanism very well, can we have a better conversion ratio? So this is that the proposal I wrote and to NSF is that we're using electrochemistry, split water to produce hydrogen. This hydrogen, we don't want to produce hydrogen gas. We want them, suppress them to become hydrogen atom. So hydrogen atom is very reactive. On this side, we have plasma. That plasma generates vibrational nitrogen that can form a surface nitride and enabling that the PA-MvK mechanism. So is this true? So we try to do experiment, and Professor Huiqing He in Rutgers University helped to synthesize tungsten oxide. And we generated plasma-generated surface nitrate radiation for the experiment. As you can see, we reached 100 times more of ammonia yield compared to the literature presented to you before. We have reached 50% of Faraday efficiency and much higher than the Haber-Bosch process. And by using hydrogen addition into nitrogen, we can further increase the yield by 5 to 8 times of ammonia with this intense surface nitridation mechanism. So, but as a function of time, this a nitrogen loss still problem. So the opportunity that in situ plasma MvK mechanism can prevent that nitrogen loss in the catalyst. So that was a proposal I submitted in March and is funded now. We have 4 people collaborate together, try to develop a plasma electrochemistry assisted ammonia synthesis. And we'll report to you in 3 years and see how far we can go. So what I try to conclude is that, you know, combustion chemistry and plasma chemistry can enable, you know, a new reactivity control and instability control. And non-equilibrium materials like ferroelectric materials can enable in plasma afterglow control and plasma reactivity control. And the new mechanism with plasma-assisted MvK mechanism can enhance ammonia synthesis and enabling new reaction pathway and reduce activation energy. And I think that the non-equilibrium process, including combustion, plasma, electrochemistry, providing exciting opportunities for innovation in net zero carbon emission, chemical synthesis, and manufacturing and recycling. Just we showed you today. My last comment is that combustion research is not obsolete, and will thrive into the green energy using the knowledge, particularly with transport and chemistry. I thank you for your attention.